Hey, what's going on, guys? What's happening? So today we're going to talk about nodal analysis. And the first thing I want you to know, right, to realize is that what's going to be important here is what I told you about before about the voltage differences, right? You're really going to, this is where the voltage differences are really going to be tested. Your knowledge of voltage differences are really going to be tested, right? Okay, so as we can see here, first thing I want to explain is what an essential node is. As you can see, LT Spice has already labeled our essential nodes. We have a square here and a square here, and basically that's what an essential node is labeled as in LT Spice. And basically, what an essential node is basically just a node, as we know, points, nodes, junctions, whatever you want to call them, that contain three circuit elements, right? So we got, as you can see, we got a resistor here, and resistor here, and it's all connected, as you can see, to this one node, right? It's all connected to this one node, right? Um, as we can see here, so let's look at this node right here, right? As we can see, well, as with this wire, this node, this point, whatever you want to call it, there's only two circuit elements here. We have a resistor and we have the positive terminal of the battery, right? There's only two circuit elements joined here. So therefore, this node is not an essential node because, again, an essential node needs to have three or more circuit elements, right? Now let's go down here, right? Well, this whole entire wire is consistent of this node, right? So it doesn't matter if we label this node here, here, or here. It's still all a part of this one wire, right? So as we can see, we have the negative terminal battery, the resistor, and the negative terminal of the other battery, right? So therefore, we have three circuit elements in this one node, right? So therefore, this is also an essential node. Now, when we're picking essential nodes, we also need to at least pick one ground, right? One place where we're going to label 0 volts. And obviously, the smartest place to label that is going to be, of course, the negative side of the battery, because we know the negative terminals of the battery is 0 volts, right? So therefore, we're going to label our ground here. So our ground is 0 volts. So let's go ahead and label that real quick. Let's label that 0 volts. All right. So our ground is labeled 0 volts. All right. Label our ground because 0 volts. Now, a thing we like to do when we're doing circuits to make our jobs a lot easier is we like to, label the voltages we know. So let's do that real quick. So we already labeled ground because we know ground is 0 volts, right? So let's label the next couple of voltages, right? So let's look at this battery right here, this 20-volt battery. Now, if we know ground is 0, right, and the negative is connected to ground, so the negative is 0 volts, and we know this battery has to have a voltage difference of 20, right? What does the positive have to be for that to happen? 20, right? Because the difference between 20 and 0, 20 volts and 0 volts is 20 volts, right? So, and that mass adds up with the battery, the voltage difference of the battery. So, therefore, we're going to label this point 20 volts because, as you can see, it's connected to the positive terminal. This point is connected to the negative, so this has to be 20 volts to accommodate for the voltage difference of the battery. So, let's label that real quick. Uh, 20 volts. All right, here we go. So, this is 20 volts. And the same rule applies to this battery right here, right? We know the ground, the negative's connected to ground. We know the ground is 0 volts, right? So, what is the voltage on this line to accommodate for the voltage difference of 12 volts with this battery? We got 0 volts here, so we must have 12 volts here. So let's label that. So we have 12 volts. So we found two voltages in this circuit so far. Now what we want to do is we want to look at our essential node, right? And obviously we don't know the voltage difference between this resistor because we got 0 volts here. But the voltage difference is, we don't know it yet because there has to be a voltage here, and then to go through here, this has to be 20, and to go through here, this has to be 12. But we don't know that voltage difference, right? So we're just going to label this. Right now, we're going to label this VA, right? So we're going to label our essential node here, VA. Now, what we're going to do is we're going to write an equation to solve for VA, right? And we can write that equation through Ohm's law. And I'll show you how to do that in a second. So let me just type Ohm's law real quick. That way we just have it for a reference point. All right. Here we go. There we go. Ohm's law. All right. So we're going to use Ohm's law, right? Now what we're going to do is we're going to envision that all the current in this whole entire circuit is going towards that node. That's what we're going to pretend like what's going on. Now, obviously, that doesn't follow Kirchhoff's current law, right? That's not happening in reality. But we're using it as a theory just so we can figure out the voltages in the circuit. Just so we can find VA in the circuit. Like this is one way. There's other ways to find VA too, but this is like hands down the easiest way because it takes the less amount of mishaps, right? Because like you can, if you do it the other way, you would mess it up a lot. So this is the easiest way to do it. So we're gonna do it this way, right? So what we're gonna do now, and just to let you know, guys know the other way. For example, the other way you would just use Kirchhoff's current law. You would do the same amount of voltage going in or leaving a node has to be the same amount coming in, right? So you would have, the same amount of current coming in has to be the same amount going out, right? So you would have a current here, right? That's going in, and then you would have a current leaving and a current leaving, right? So you would use Kirchhoff's current law, and you would solve it through that way. So yeah, that's how you would do it. But like, we're not gonna do it that way because you can mess up a lot. So let's start doing it, the theoretical way. So we're starting at 0 volts here, right? We start at 0 volts. When we go to 0 volts, right? So we went from 0 volts through the negative terminal battery to the positive, right? So we went from from low potential to high potential, right? So that's going to be a voltage lift. That's going to be a voltage lift of 20 volts, right? So we have 20 volts here, right? Now, if we know how electricity flows, right? Electricity travels from low potential to high potential, right? Same, just like how I did here, right? Now, again, this isn't happening in reality. In reality, the electricity is going this way, into this way. But just you know, for the sake of solving this problem, we're going to pretend like the electricity traveled from the negative terminal to the positive terminal of the battery, right? And now we have 20 volts here. Now, when we keep following this line, right? Now, the electricity is going to hit a resistor, right? So that means Ohm's law has to take effect on this resistor, right? So, to find the current in this whole entire wire right here, which is what we're trying to do, we're trying to find the current in this whole entire wire right here, right? Hold on, so let me get rid of this. So what we're gonna do is we're gonna subtract the low potential of the resistor to the high potential of the resistor, right? Because remember, as we said, electricity travels from low potential to high, right? Low to high. It's gonna travel from low to high. So we hit the low potential here is 20 volts, and the high potential here is VA, right? So what we're gonna do is we're gonna find the voltage difference between this. How do we find the voltage difference? Well, the formula for voltage difference is gonna be the high potential minus the low potential. So let me write that real quick. I'm going to write that up. I actually want to keep those there. So let me keep that there. All right. Actually, I can just do a minus and a plus. That would be a lot more easier to keep track of. Let's do minus, do plus. All right, there you go. Minus plus. All right. So the formula, let's write the formula now for voltage difference. So voltage difference equals the high potential. Um, yeah, let's just write it that high potential minus low potential, right? This is what voltage difference equals, right? Voltage difference equals high potential minus low potential. So as we can see, VA is going to be the high potential here, and 20 volts is going to be the low potential here. Let me see how much time I have on my recording. Okay, I still have good times. All right, so what we're going to do here is we're going to do VA, which is the high potential, minus 20, which is the low potential, right? We're going to do VA minus 20, right? We have VA minus 20 here, right? Now, we want to find the current that is traveling through this entire wire, right? Because, all this wire is basically a series circuit. This whole entire wire right here is a series circuit, right? So, what we want to do that, obviously, is we take the voltage difference of the battery, right? Okay, hold on. Let's do that, right? Let's write that equation down. So VD divided by the resistance equals I, right? We can also look at it like that, right? VD divided by the resistance is going to equal the current that's in this node, right? So I'll label the current IN, just so like you guys get used to mathematical terms, and I'll call it RN too, or I call it W. Let's call it W for the wire. Right. So the voltage difference divided by, we'll call this VDR too. VDR for voltage difference across the resistor, right? So we have the voltage difference across this resistor divided by the resistance of the wire will equal the current of the wire, right? That's our equation we want to remember, right? So, because using Ohm's law, right? Voltage divided by resistance is going to equal current, right? But in this case, it's not going to give us, like, the current of the entire circuit. It's going to give us the current of the voltage. I mean, it's going to give us the current of the wire, right? The current of the wire. So let's do that real quick. So we're going to do, so we did the voltage difference across the resistor, divided by the resistance of the wire, which is 10, of this wire right here, this entire wire right here. The resistance of this entire wire right here is 10 ohms, right? So we have a 10 ohm resistor on it. So we're going to do that. We're going to divide that, and that's going to give us the current of this wire, right? So let's do that. So we're going to do VA minus 20, right? Let me put this in parentheses, just so like, All right, divided by VA minus 20 divided by R1, we'll say. And that is our first equation for this, right? That's going to be our first equation. So let me actually label this, right? So that way we keep track. We're keeping track of stuff. All right. So what do I want to do now? So I want to move this right here. There you go. All right. So we have our first equation right here, or our first expression, because this is going to be a giant equation. So let's see that. All right. So we have our first equation, first expression of the equation. Let me see what my time is looking like. Right, we got 12 minutes. I may end the recording here, but we'll see if I can get anything else done. All right. So we did that equation for this part of the wire, right? So this part of the wire is complete. We did this part of the wire, right? This part of the wire is complete. So we're going to, I don't know, like what can we do for it complete? I don't even think that exists on the keyboard, but oh well. So, yep, I'm going to continue this recording because I'm about to run out of time. So I'll continue this recording in the next video.